Hello all, we are team Dual Course. Myself, I am Mari Venkatesh M, along with my friend Aditya Ram. So, our hackathon project name is FPGA-based Siren Detection Accelerator for Smart Traffic Management. So, this would be our video demonstration. And before we get into the video demonstration, I would like to explain a few things about our project scope. So, okay, can you tell me which of these two sound is an ambulance siren? I mean, if you are looking at the top rows, the audio raw audio amplitude, you genuinely cannot tell both. I mean, both are just loud, chaotic burst of noise. The car horn on the left and the ambulance siren on the right. They look practically identical to any standard signal processor. Volume alone is useless. This is exactly why naive CPU based detector fails in this real world. Now look at the bottom rows. This is the car horn after our hardware accelerator does the fast Fourier transform converts it into a frequency domain. What you see is a flat static energy distribution. Energy distribution, the broad spectrum noise with no structure. The energy just sit there spread across frequency unchanging over time. Now look at the ambulance siren. See that bright diagonal uh, rising from the bottom left to the upper right. The energy starting at around 500 hertz and swooping upward towards 1500 hertz over time. That is the cycle of a real emergency vehicle siren. Every country standard siren does this. It is physically, geometrically distinct from every other sound, urban sounds. This is the core inside of our entire system. We are not listening for volume. We are looking for a shape, specifically this diagonal sweep in the frequency domain. And critically, we restrict our MEL spectrogram to only capture frequencies between 500 and 2000 hertz. This is deliberate domain knowledge, band pass filter, and everything outside the range. Drilling, dog barks, music is rejected before our neural network process a single number. This chip never sees any irrelevant data. Okay, so this is our Vitis HLS, and we just saw about the importance of the signal, and I also explained about the problem statement. So in our software pipeline, we did the feature extraction, that is the DSP, and followed by the 1D CNN, and we did also did the accuracy, F1 score, and recall everything, and it's all documented properly in our technical report. So after that, we exported the weights of header file, and you could see this. And now we are in here in our Vitis HLS. So okay, so now what you are looking at this the core of our system, the HLS C++ file, this one. So this would be our core system. This code was synthesized by Vitis HLS directly into the Verilog RTL and physically deployed onto the programmable logic fabric of our Zynq processing system. And let me walk it through you by layer by layer. So you could see a function, a void siren underscore hw underscore block. So this takes two arguments, a 128 element array of int 8 audio feature and a pointer to a single output byte that will hold our single output byte with which could hold our detection result, 1 for siren, 0 for normal traffic. Okay, so pragma this pragma directive defines the hardware um, interfaces. The audio feature arrives via an AXI stream port. It's an important protocol under the AMBAS. A high-speed streaming bus from DMA engine. The output and control signals are mapped to an AXI light um, register interface that the ARM processor can pull. So coming to this important, this is considered to be one of the important decision architecture, that is the unload the conveyor belt into a local self BRAM. So I'll explain it. Okay, so what this basically here happens here is, see this copy loop. We take the 128 incoming uh, audio features from the AXI stream interface and copy them once into a local array called a local audio. This local array gets synthesized into a on-chip block RAM, the BRAM itself. Why does this matter? Because the alternative reading directly from the AXI stream inside every iteration of a convolutional loop would require a AXI handshake for every single memory access. Our convolution loop has four nested level, 32 filters, 8 steps and 16 channels. So 8 into 16 that gets 128. And 3 kernels positions that's 32 times 8 and yeah. And finally 12,288 inner iteration, each of which would stall on an AXI handshake delay if we didn't buffer first. By copying once to BRAM and reading from there, we reduces 12,228 potential stall down to essentially this 128 initial transfer. The convolutional kernel then run at full speed, and this makes our whole process a smoother way. Okay, so down we could see the neural network part. So we build this in C++, and layer one is the 1D convolutional and 32 filters. Yeah. So okay. So this is the 1D convolutional program, and we uses the ReLU as our activation and max pooling, the layer 2, layer 3, dense. And this is an overview of our complete code.cpp. And here you could see the if siren is detected, that's equal to 1, and if siren is not detected, that's equal to 0. So this complete siren have a stride of 1 and paddling of 1, and the kernel size is 3. So this is our test bench that we created inside our Witness HLS. So we are not using a synthetic data. So basically, you don't just confused. I mean, why this numericals? This is not synthetic data basically at first place. And this 128 element array of int 8 values. These are negative numbers or real extracted audio from it directly from sample from the Urban Sound 8K dataset. That is a predominant dataset that we use on Kaggle. And this is an actual siren frequency sweep block. Looks like a resampling to 8000 hertz, applying our 500 to 2000 hertz band pass, mill spectrogram, and quantized to 8-bit integer. We initialize the output to -1 deliberately. That way, um, if the hardware never writes to it, we know something is broken. It cannot accidentally produce a false pass, by the way. We fire the hardware block, then check the output whether it's 1 or 0. Any other value means the hardware produce and corrupt output. That is not that's not the way we decide. And the test only passes on a valid boolean. That's the 0 or 1. And this test bench is the C model that British HLS uses to run co-simulation, and that compares C model output against the synthesized RTL output cycle by cycle. Okay, so as I discussed about this 128 bytes, so what I'm gonna do is now let's have a look on this synthesis summary. Okay, so this is what I did after the synthesizing, and it went perfectly fine. I didn't get no errors, and you could see the time estimate and everything. So this is the demo for I mean in Vitis HLS part, and this is the latency cycles of 3900 and BRAM utilization of 32 and DSP of 80. So now it's fine. We synthesized without an error, but still, for a quick sanity check, let's have a plot and make sure whether everything works perfectly. So for that, we'll go to this thing called run core simulation. Let's see. So yeah, so after the simulation result, we could see the status is passed. So that means our work is done perfectly, and this is what we actually expected. So let's also cross check for a quick sanity check. Let's go and view it in a waveform viewer. It will take a little bit time to open the Vivado pod. Okay, so finally the waveform viewer have been opened. So now let's go directly into the output. We could see the siren detector. This is basically a trigger, you know. Um, let's see. Okay, so you could see it after it got triggered, and this is basically the processing time. And you could see it's in of the nanoseconds, and you could see it's one. So one in the sense the siren is detected. So we confirmed it. It's working perfectly fine by the British HLS co-simulation test, and also using the waveform viewer. You could see the result. Okay, so we saw that we actually did the co-simulation part and it went perfectly fine. So what we did is after that we export that RTL and that is our custom-made IP. And using that custom-made IP, we opened the Vivado and we did the necessary. I mean, we did the basics of all the IP block diagrams, and we generate the bitstream and all the data regarding the implementation design, LUTs, BRAM, static power, and everything was clearly explained in the technical report. And now let's jump directly into the demonstration part. And for this we are using a Z board and it is connected to our system. So let's have a look on the Explorer. I mean, we have this uh, design wrapper that we got it from the Vivado, and we generated the bitstream, and it's worked completely fine, and we exported into the Vitis. So let's no update the hardware if in a case. I think it's fine. It's perfectly fine. Okay, okay. So then I'm going to the Siren app. Yeah, updated. So I'm going to the Siren app system launch device. So um, so program. So in this case, if it's working fine, then I will see a blue color light blinking in my Z board. In my case, it's blinking. The video will be yeah, it's blinking. So now let's go to the Vitis serial terminal and make sure the baud rates are perfectly fine for the UART protocol to establish. So click OK. So connected to COM7 at the particular baud rate. So then we go to the Siren app, go for build project. Yeah, so we built it already, and we will show in this video for it. Okay, so after the build finish, now we click the Siren app, go to the debuggers, and do launch hardware. And for the same, we connected to our Z board. Basically, we dumped the code and generated the bitstream, and we are checking for whether the whole all of our whole works are perfectly working fine at the hardware silicon level. So this is the main.c code, and this is the extracted siren siren signal that I discussed already. And so okay, so this is the console. Basically, whatever the we are trying to print using the xil underscore printf will be printed in this particular console, and we could see. Okay, so I'm going to this step over, and you could see it's getting printed in this console. So I also made sure my board is connected to the system and the blue color light is blinking. That means it's working perfectly fine. So let's go for it. So the AI calculation hardware is completed, and this is the crucial. So when I reach this, we actually completed this line, AI hardware calculation completed. In that case, we could see the variable block. You could see it came to 0x001. That means it detected the hardware detected our the actual siren. And it's detected the memory, but still we'll see whether it's printing in the console. Okay, so again I'm doing the same step over. Yeah, perfectly fine. It got printed as siren detected. So it works perfectly fine, and this is our video demonstration which we got connected to the Z board. That's what we are using, and thank you.